Moving on, we're now going to talk about equipotential lines. And those are lines that represent spots that have an equal amount of electrical potential and require no work to move along. So we have a point charge Q, and we see the electric field lines in blue moving out from the positive point charge. The equipotential lines are shown in green. The potential along each of these lines, which are circles, is the same, meaning that no work is required to move a charge around that circle. However, if you want to move from one circle to another, then work has to be done. The equipotential lines are always perpendicular to the electric field lines at every point. Grounding is a situation where you fix a conductor at 0 volts by conducting that conductor to the earth, which is a good conductor. So when you put a conductor to the earth, then you fix that at 0, and then that's called grounding. Here's a situation where you have a positive and a negative charge in the representative field lines and equipotential lines. The field lines and equipotential lines are equal but opposite when you have two charges. The lines are drawn and they have to be perpendicular at every point where they cross an equipotential line. Notice that the potential is greatest, that is most positive, near the positive charge, and least or most negative near the negative charge. And here you have another situation, but in this case, you have two negative charges, and you can see on A that you have these equipotential lines. The farther you get away from the negative, the less the potential is at that point. The equipotential lines could be measured by a voltmeter in a laboratory. The field lines are drawn, and again, they have to be perpendicular to the equipotentials at every point. The fields are consistent with two negative charges. Now here you have two parallel plates, and the electrostatic charge lines represented in blue moving from the positive plate to the negative plate, and the equipotential lines drawn in green. And again, you see that one side is 0, the other side is 100, and you have various voltages across the top. The electric fields and the equipotential lines are shown between these two plates. Now, a capacitor is a device that is used to store electrical charge. A capacitor is a device that's used to store electrical charge. It's used in devices that are not necessarily hooked up to any electrical source. So you can add charge to it, and then it will, in a controlled fashion, discharge that charge when needed. The charge of a capacitor is stored, and it's stored based on two factors. One is the amount of voltage that is applied, and the other is the physical characteristics of the capacitor, such as what the capacitor is made of, how large it is, the distance between the plates, etc. Both capacitors shown here are uncharged when they're not connected to a battery. When they're connected to a battery, they develop a charge between the two plates. The top one is called a parallel capacitor for obvious reasons. The bottom is called a rolled capacitor and has an insulating material between the plates to prevent discharge. The field lines of a parallel plate capacitor start from the positive side and end on the negative side. The field strength is proportional to the density of the field lines. It is also proportional to the amount of charge on the capacitor. That is to say that the greater the charge on the capacitor, the greater the electric field and the greater the number of field lines. And capacitance, which is a measurement of how much charge the a particular device can hold is equal to the charge of the capacitor divided by the potential difference between the two plates. So 1 Faraday, and Faraday is the unit of capacitance, is equal to 1 coulomb divided by 1 volt. Now, as I said before, the capacitors, one of the things that determines the amount of capacitance is physical characteristics of the capacitor. And this formula shows those physical characteristics. A is the area of the plates, D is the distance between the two plates, and E0 is called emittivity, and it is a function of the material between the two plates. The E0 in a vacuum is equal to 8.85 times 10 to the minus 12. Now you can put different materials between those two plates and change that E value. And this is an example of a couple of different materials that you can put in there. A is called a dielectric, and a dielectric is a material, insulating material, that is used to separate the two plates and avoid the breakdown of those plates, and it has an impact on the ability or the capacitance of that capacitor. The capacitance is then calculated by E0 times a K, which is the dielectric constant. So that is the change in the ability of the charge to travel across based on whatever that is made of. So you have K E0 A over D to measure capacitance. The molecules in the insulating material between the plates of a capacitor are polarized by the charged plates. This produces a layer of opposite charges on the surface of the dielectric that attracts more charge onto the plate and increases its capacitance. So as you can see, that many of these factors, many of these dielectrics improve the capacitance and storage ability of the capacitor. However, some dielectrics reduce the field strength inside the capacitor and result in a smaller voltage between the plates with the same charge. The capacitor stores the same charge for a smaller voltage, implying that it has a larger capacitance because of the dielectric. Now, this is an artist's rendition of what happens when molecules are polarized. And the dielectric strength is the maximum field strength above which the insulating material can no longer act as an insulator and becomes a conductor. And I told you what that was. This is another artist's conception of a water molecule and the polar nature of water. So let's take a look at a couple problems related to this, to the measurement of capacitance. Find the stored charge when a 12 volt, 5.5 volts is applied to an 8, and P stands for pico, or 10 to the minus 12, picofarad capacitor. So we remember that C, it's the charge we're looking for. Q is equal to CV. Remember, C was equal to Q over V. And so Q is equal to CV is equal to 8 times 10 to the minus 12 picofarad times 5.5 volts equals 4.4 times 10 to the minus 11 coulombs, or 44 picocoulombs. Now the second question here is, what is the capacitance of parallel plates having an area given here separated by this distance of neoprene rubber, and it gives the K for neoprene rubber as 6.7. Well, we remember that capacitance is equal to E0 K times A over D. So that's going to equal 6.7, and E0 was 8.85 times 10 to the minus 12, and the area was 1.5 meters squared. All of that divided by 0.02 times 10 to the minus 3 meters. And if you do the math here, you get 4.45 times 10 to the minus 6 Faradays, or 4.45 microfarads. Now the second part of this question, what charge does it hold with 9 volts applied to it? Well, remember that Q was CV. So we had 9 volts applied to this 4.45 times 10 to the minus 6. And so that's going to equal 4 times 10 to the minus 5 coulombs of charge. Now we can set up capacitors in either series or parallel. And this is an example of setting up a group of devices, capacitors, C1, C2, C3, in series. That means they're all in a row. And in any situation where you set up capacitors this way, or resistors, or anything else, you can substitute for the 3 different capacitors one single capacitor called C sub S, sometimes also called CE, standing for the equivalent capacitor, if you had just one capacitor. And basically what it does is it tries to represent the total distance between the two. So if you connect these in series with a certain magnitude of charge on each, the equivalent capacitor would be equal to the enlarged distance. And the calculation is shown in the subscript C here. 1 over CS is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So CS is going to be, once you find that sum, then you have to take the reciprocal of that to do the calculation. Now the other way that this can be done is to put them in parallel, which is shown here. And when you put them in parallel, it increases the charge, keeping the distance the same. And so the equivalent is as if you have a larger plate with a greater charge with the same distance between the two. And so C sub P here, which is also the equivalent if you substitute, is equal to C1 plus C2 plus C3. Now, if you have what's called a combination, the way that you work a combination is you find the first equivalent. Going from A to B, you would basically do 1 over 1 plus 1 over 5 is equal to 1 over CS, and find CS at that point. And then those two, CS and C3, are in parallel. So the equivalent, C, is going to be the sum of C sub S and C sub 3. So let's finish up by doing a couple problems related to this. What is the total capacitance you can make connecting a 5 microfarad and an 8 microfarad capacitor together? Well, you can connect these together in 2 ways. first of all, you can connect them in series. So for example, and if you connect them in series, 1 over CS is equal to 1 over 5 plus 1 over 8. The least common denominator between these two is 40. And so it's going to be 8 plus 5, or 13 over 40. Now that equals 1 over CS. So CS is going to be 40 over 13, or approximately 3.0, about 7. Let's see what the microfarads. So if you connect these two in series, that's what you're going to get. In parallel, you connect them in parallel, and it's just 5 plus 8, or 13 microfarads. So that's the simple one. Now let's move over to this more complicated one here. We have this diagram here, and I'll be switching back and forth between here and here. First of all, you could either do this one part or do this part. These two are in Faraday. It says, what is the equivalent capacitance of all the capacitors are 5. Well, if you start with these two, they're in parallel. And that's C1 and C6. So we'll call this C16. That's going to be 5 plus 5, or 10. Okay? So that changes this to a single one that's 5 plus 5. These two are in series, and we'll call that C35. So C35 is 1 over 5 plus 1 over 5, or 2 over 5. So that's 1 over C35 is that. So C35 is going to equal 5 over 2, or 2.5 microfarad. So that's this one right here. So now you have these three, this one, and this one. So C4, C35, and C2 are in series, or in parallel, excuse me. And so C2, 3, 4, and 5 is going to be 2.5 plus 5 plus 5, or 12.5 microfarads. And so that really combines all of this. And remember, we had this already. That was right there, up here, I mean, right? And so now this one and this one are in series. And so we'll call it the total, or the equivalent, is going to be 1 over 10 plus 1 over 12.5. And there's a couple ways you can do this. You could say this is 0.1 plus, and if you take the reciprocal of 12.5, that's 0.08. So that's going to equal 0.18. And that's 1 over that. So CE is going to be the inverse of 0.18, which is 5.5555, or 5.56 microfarad. So the one equivalent capacitor that would equal this entire diagram is going to be 5.56 microfarad.